We just said that we are concerned about steady state, and you just have to record the values and in the steady state. But now we are paying attention on transient state too. What is transient state and steady state? So transient state or period is one where a DC signal does not change with time. Like when you have not applied voltage, that is a steady state. But when you have applied voltage and voltage started increasing, that's not steady state until it reaches a certain value. Like here, they are assuming that your capacitor is at 10 volts, let's say. So until unless it is at 10 volts and does not start discharge, it is the steady state. But when it start discharging or charging, that is a transient state. So it's important to know how can we check the transient state, okay? Or how can we measure the changes that are happening in the transient state. So let's see. Okay, so first transient state is that your RC, your capacitor starts charging, right? So when you apply voltage, you see change in your voltage, and that change is not linear. It's actually pretty exponential. So that's what it says, that you know that when it starts charging, it says actually we say that okay, 1 tau it will reach at 63% of input voltage, 5 tau it will reach at 100% of its input voltage. So that's what this graph is showing. But another thing we saw that if our resistor is greater and our capacitor is greater, we will see the curve that will not be as steep, but the curve will be like that. So it will take more time to reach its input voltage, right? So that's what the charging and discharging graphs look like. It's like the exponential decay or exponential increase. So I'm not going into detail how you get the this charging voltage. I think we will learn it ENG 212. So we will just see that what is this charging voltage is, how can we measure it? So this is RC charging voltage. When a capacitor starts to charge, when you plug battery in, and this is the charging voltage across the capacitor, where T is the time, okay, and RC is the time constant. So RC is constant, Vs is the source voltage, and T is the time. So it means that, let's say you have, like you are recording time and you pass 10 seconds. So you can just replace 10 seconds here, multiply by your source voltage. So the voltage that will appear, that you will calculate from here, should be equal to the voltage across the capacitor. Similarly, as of course, as the voltage increases, current decreasing. So as soon as voltage starts approaching towards the input voltage, there will be no current that will be flowing, right? So that's why it's acting as an open circuit. So this is the current. So what we are pointing here, that as after 1 tau, your voltage will be 63.2%, but your current will be 36.8% because it's decreasing. So that's the formula for current. Because it's an exponential decay, it's I naught E minus T by RC. I am just going through again what we are expecting in the current and voltages. So if you have the square wave input, you are seeing that your voltage across capacitor increasing exponentially and decreasing exponentially, and your voltage across resistor is decreasing exponentially, which is the same curve as your current, because your current also starts decreasing exponentially as your voltage starts increasing. And at this point, it's almost zero, right? But when your capacitor starts discharging, it reverses its polarity, current, if you're talking about current, and starts increasing again. So that's what it's about. Like that's what the curves are about. So that's is important to know. So again, I'm talking about this curve, that how this in this curve we should be familiar with the percentages. So after one tau, if something is decreasing like current or voltage across resistor, it should be 36% of its input voltage, and if the it is increasing, it should be 63% of its input voltage. Okay, so now when the capacitor starts discharging, its curve is like that, and voltage is E minus T by tau, which is the same as when the we were seeing decaying current, right? So the voltage across capacitor will be the same. So today we will be doing this experiment in which we will pay more attention towards the transient time. We will see that how capacitor acts in the transient time and how we can see the changes that are happening in the circuit. So if you see in the 16th experiment, you are seeing procedure number 1. You are seeing a circuit in which you can see 2 capacitors, right? So how we will calculate charging time now? The charging time will be the equivalence of these capacitance. So then you can calculate, you have to calculate total capacitance, time constant, charging time. That's what it says in the part D, and you have to fill this table in. So let's see. What I tried to put here. So as these capacitors are parallel, we know that when the capacitors are parallel, we can just add them. I just added a note that here we want to take both of the capacitors at 100 microfarad, and our input voltage will be 9 volts. So it's for both for simulation and for experiments, okay? And you can see that resistor value and capacitors values are higher, which will make time constant higher. So it will not be, you know, like in blink of a second, your capacitor will be charged. It will take time. So you can record values. What do you think if you apply this formula, like your capacitance is C1 plus C2, and your tau will be RCT? What will be your tau of this circuit if you are using 100 microfarad and 100 microfarad here?
$200 microfarads times 100K.
Yes. What it will be? $200 into 100 is 20.
Yeah, 20.
What you said, 20 what?
I think isn't it just 20?
20 seconds, right?
Yeah.
Okay, so it's 20 seconds. One tau is 20 seconds. So it means that in 20 seconds, it should reach 63% of its value or input voltage. That's good. So what I'm seeing here is in table 16.2, what you need to do for all the seconds, you will record voltage across capacitor and VR. VR, you don't have to do. What you just do, record VC, voltage across capacitor for all these seconds, and just do E minus VC. That will give you VR. So it's okay. You just use the measured values to calculate a measured VR. And then you will plot the graphs on 16.1, and you will label what is 1 tau and 5 tau. So someone says 20 second is your 1 tau. So what is your 5 tau should be? What should be the value of 5 tau?
100 seconds.
100 seconds. So if you see the graph, it is up to 200 seconds. So you can point it out that at 100 seconds, that reaches its maximum value. I'm not sure that that's what value you will get in measurement. Maybe your capacitance value vary because of tolerance and resistance value vary because of tolerance. So, but that should be, you know, approximate values that you will get. So, what is the value of VC after one time constant that you need to record? Okay. So what I am just showing here that your calculation should show that after 10 seconds, E into 1 minus E minus 10 by RC should be your V naught or VC. Okay. Understood?
Yeah.
Okay. So this is the second circuit, that is procedure number 2. Okay. In procedure number 2, you have 2 resistors and you have 2 capacitors. Now your capacitors are in series, which means that we have to calculate equivalent capacitance, and then resistors are in series too. So in this experiment, in this procedure, your equivalence capacitance should be like this, and your total resistance is RT is equals to R1 plus R2. You again calculate tau, and you will do V naught is equals to E1 minus E minus 10 by RC. And similarly, you will fill the table. We will not be doing procedure number 3, but we will be doing exercise. In exercise, you will leave question number 2, because that will I will discuss in next lab. Other than that, you will do exercise and procedure 1 and procedure 2. You don't have to do procedure number 3. I will show you LT-SPICE simulation for procedure 1. So is that clear till now?
Yeah, so we'll have a simulation and a lab report for this one.
Both, for both.
Mhm.
But
And,
I will be showing procedure 1, yeah.
and we don't do procedure 3 or exercise question 2.
We will not do procedure 3 and
Yeah.
number 2 question of exercise. Yes.
Oh,
Okay. Sounds good? Okay, let me show you how we will do LT-SPICE. Okay. So I want to do procedure 1. Okay. My C2 is 100 microfarad. Okay. And I will go to the voltage pulse. Initial is 0, on is 9, delay is 0. You know what is this? I mean, how I enter these values? Okay, so you calculated 1 tau as 20 seconds, let's see. Okay, so tell me what should I enter here as T on? Because T on is the time which will give 9 volts to the circuit.
A 100 seconds.
Okay, let's see. Mm. Okay, so let's see. Okay, you can see now. Why you think 100-second is fine time? Herschel,
Yeah.
why you think we should give 100 seconds here?
100 provides a smooth curve and it reaches the peak at that time.
Yeah, because 100 seconds is approximately equal to your 5 tau, right? And if you see, if you want to see what you are getting at 1 tau, let's see. 20 seconds, right? Something about in between, what you should say, 5.9 volts and 5.5, something like that. You are getting in between that, around at 20 seconds. Okay, so what I'm saying that you just have to show this. Okay, you have to show this that why I do you know? I mean, do you understand why I took 200 seconds here?
Could you?
Chris? Yeah, yeah. Go ahead, Sam.
No, I wanted to ask if you could explain it again.
Okay.
I know you're asking us, but
It's okay. I just want to know, Benjamin, what do you think? Are you here? Maxwell?
Is the amount of time for the capacitor to load and then unload?
Yeah, that's true. That's right. Okay. So Sam and anybody else who want to know. So what we are doing here is that we said that RC is actually, our RC is 20 seconds, right? So 20 seconds is the time when voltage across capacitor should reach, just a minute, I can do this too. Voltage across capacitor should reach its 63% of its value. So RC is the time when it should reach 63% of its value, okay? So 63% of 9 volts is what? Sam, what is 63% of 9 volts?
it's 5.67.
5.67. So you should see 5.67 around 20 seconds. Okay? Something here, okay? You see what I'm saying?
Yep, you see it.
Sam, do you think it's fine?
Yeah, you said in 20 seconds. So it takes 20 seconds for it to reach 5.67 volts.
Yeah, why? Why I said that?
I guess that's what I'm trying to figure out.
Because it's 63% of input voltage. Okay, let me show you again what I'm saying.
So, okay, I get the 63.7, that percent of the voltage. So it's 20%. It's 20 seconds because of what exactly?
Just a minute. So we know this graph, right? So what I'm saying here is that this is your point when you are getting 63% of your input voltage, right? So which is, you are saying 5.67, right? But when it will occur at 1 tau. 1 tau is RC, and RC in this circuit is 20 seconds.
All right, I got you.
So at 20 seconds, you should see 63% of your input voltage across the capacitor. Okay? Sarab, do you think it's fine? Sarab, are you here?
Yeah. Yeah, I think I'm good.
Okay. Adeline, you think you're good? Eunice?
Yeah, I get it.
Okay. So that's what we were saying, that it should reach 63% of its input voltage here. That's what you were saying as 5.67. So it should be somewhere here, okay? Then what is 5 tau? Someone said to me that you should keep this 100 seconds. Why he said that I should keep this 100 seconds? Because 100 seconds is 5 tau. If I keep it less than 100 seconds, I will not give capacitor fair amount of time to charge itself. If I keep it more than 100 seconds, it will charge and become at steady state and then discharge afterwards. Let's see, we can do that too, okay? So let's keep it 500 seconds, and this would be 1,000 seconds. Then this will be, let's say 1,000 seconds. Okay, and run the simulation. So you can see what is here. Till what you are seeing, you can see where is the transient time here and where is the steady time here. Nitya,
Sorry, could you repeat that again?
what is the transient time here and what is the steady time here? It's okay. Thomas? Amanda? I cannot hear you. It's okay. Okay. Anybody knows what is this transient time here and what is the steady time here?
Is the transient time up until the curve flattens?
Yes.
Which is 0.1 ks.
Yes. So
then-
transient time is this one, because here you can see the change is happening. And steady time is this one, where it's at the same point that your capacitor voltage, right? Understand?
Yeah.
Similarly, here you can see the transient time here. And after that, this is the steady time. So that's what we are trying to see here, that how we can see the change in voltages in transient time. Got it?
Yeah.
Mm-hmm. Eric, you good?
Yep, I'm good.
Okay, so that's what you guys have to do. I mean, you don't have to show me that this is the transient. I mean, if you show, it's fine, but if you don't want to show me, it's fine. But what you have to do, complete your measurements and compare your calculations with your simulations, okay? Your simulations should show that you have given good amount of time for your capacitor to charge and then discharge. Okay, you don't have to show me that, oh, we have changed times and that's what happening. It's good to know, but the least that I want to see from your simulations is that you have pointed out that, okay, here, this is the 63% of charge voltage I got from simulation, from measurement, and from calculations. Okay, and similarly, here is the 5 tau. So what they ask you to do in measurements, you should point it out in your simulation report that, oh, we are getting the similar thing. Okay.
So the comparison to the actual and simulated, we write in the simulation report?
Yes. So what you are getting from your simulation, you will write it in your simulation report. Yes.
What about the comparison to what we get from doing it ourselves? Do we
So-
put that in the lab report?
Yeah. Yeah.
Okay.
Okay. I mean, I just don't want to keep it very strict. Whatever feels right to you, you can do, but simulation report should, it contains simulation. It should have the pictures of your result and how did you set up the value. And when you are doing comparisons, you can show your comparison in your lab report or simulation report. It's up to you. Okay.
Okay, thank you.
Yeah. So, but you should fill this graph, and if you want to put the scanned copy of this graph, it's okay. Okay. You don't have to draw it again. Just fill it on the book and put the scanned copy on your lab report. Okay.
So you don't want just a screenshot of this in our lab report? You want us to draw it?
No, I'm saying the screenshot is fine of the graph, 16.1.
Okay.
Okay. Sounds good?
Yeah.
Okay. So I think that's about it. Any other question you have? If you have any question, you can ask me regarding the circuit building. It's not difficult because you just have to do capacitors in parallel and resistor in series and voltage source. So I just expect you guys to start early, even if you have time to do right now. I'm here and you can ask me questions, okay? Sounds good?
Yes, thank you.
Yeah, that sounds good, Professor.
Okay, number 2 of procedure 3 is what? Oh, someone answered it. No, number 2 of procedure 3 is not a right answer. We are not doing procedure 3. We are not doing procedure 3. And we are not doing number 2 question of exercise. Okay. I'm writing it here too, so it may be clear. You don't have to do these two things. Okay, so I am turning off my video. I'm here. You can ask me questions when you are doing your experiment. Okay.